Okay, so am I audible? Okay, let's wait for 1 minute. It's already 4:04. Okay, so I'll start. So I'm Subrata Samanta and I'm your one of the TA for the thermal physics course that is taken by Professor Demalla Banerjee. Okay, so I'm conducting these problem solving sessions every Sunday at 4 p.m. Okay, so if you have any questions, you can ask directly in these problem solving sessions. So today I will solve assignment 3 problems. Okay, so let's first share my screen. Okay, I hope my screen is visible now, right? I hope my screen is visible. So I will solve some previous year assignment 3 problems. Okay, that helps you to solve this year assignment problems. Okay, so assignment 3 problems, I mean the assignment this year assignment 3 problems is due date 12th February. Okay. So the first problems, if you look into this, so I hope my screen is visible, right? So I'll solve these previous year assignment problems one by one, okay, in details. Okay, and if you have any questions, you can ask, or if you have any questions from the week content, you can also ask. Okay, or any lectures, previous assignments, assignment 1, assignment 2. Okay, so if not, then I will start. Okay, so in the first questions, the question is that determine the mean free path of air at STP given that viscosity eta, right? So the values of viscosity is given and the mean velocity is also given and the density is given, right? And you have to calculate the mean free path, right? So how to calculate the mean free path? So the first ones, what are the quantities are given? So, okay, so let's go into this. So this is 3.1, let's say 1. Okay, so the quantity is given is the eta, the viscosity. Okay, so viscosity eta is given. Okay, so the values of eta 1.7 times 10 to the power minus 5. Okay, so these three quantities are given: Newton second per meter square, Newton second per meter square, and the other two quantities are the average speed, right? So the mean velocity, let's say C average is 4.5 times 10 to the power 2 meter per second. Okay, another quantity is rho, the density. So rho equals to 1.29 kg per meter cube. Okay. So you want to calculate mean free path lambda, right? So I am copying this. So this is the questions. Okay. So now I want to solve this. Okay. So these three quantities are given. We have to calculate the lambda mean free path. So lambda is the mean free path. So how to calculate lambda? So this is the density and this is the mean speed, mean velocity. Okay. So first of all, in the previous day, I'll discuss that the viscosity lambda eta, this is equals to 1 over third. Okay, so 1 over 3 m times n lambda C average, right? So the mean velocity, lambda is the mean free path. Now what is m and n, right? So m is the molar mass, right? The mass of the molecules, and eta is the density, is the number density, right? Now rho is the mass density, okay? So rho equals to m times m. So molar mass times number density equals to mass density. Okay? So this density is the basically mass density. Okay. So it can be written 1 over 3 rho lambda and then C average, right? So her C average is the mean velocity. So now what are the which quantities, the values of which quantities are given, right? So eta, so the values of eta is given, the values of C average is given, the values of rho is given. You have to calculate lambda. So now let's calculate lambda. Okay, so the lambda equals to 3 times eta over lambda, sorry, yeah, so 3 times eta over rho times C average, okay, or the C mean. So now plugging these values, so 3 times what is the values of eta? So here I am using the SI units, okay, so this the density is basically kg over meter cube and velocity is the meter over second and the viscosity is Newton second per meter square, okay. So all are in the SI unit, right? So then if you plug this value in the SI unit, so 3 times 1.7 times 10 to the power minus 5 over what is the values of rho, 1.29 times C average, right? So 4.5 times 10 to the power 2, all are in the SI units. So what is the unit of lambda then? So lambda is the mean free path, okay, is it basically kind of length, okay. So in the SI units, what is the unit of length? It's meter, right? So it's meter. So now you just calculate this value numerically, okay. So it gives you 8.78 times 10 to the power minus 8 meter, right? Now check this answer is in the option or not, okay. So 8.78 times 10 to the power minus 8, 8.78 times 10 to the power minus 8, yeah. So the option C is correct, right? So in the second question, okay, so if any questions so far? Okay, so I move to the second questions. So in the second questions is that the thermal conductivity of a gas at temperature T is K, okay. So this is the important. So one is the thermal conductivity of a gas at temperature is K. At what temperatures the thermal conductivity is doubled, that means 2K, okay. So let's say I have a temperature T, the thermal conductivity K, okay. At what temperature T2 the thermal conductivity is 2K. Now I have to calculate T2. Okay. So let's say at T2 temperatures the thermal conductivity is 2K, okay. Now I want to calculate what is the values of T2 in terms of T, okay, in terms of T, because options all are on the options in terms of the T temperatures, right? So I have to calculate T2. So now how to calculate? So first of all, so the first step is that to write down the formula of the thermal conductivity, okay. So the second problem, so first we write down the what is the expressions of the thermal conductivity or the formula of the thermal conductivity. So the thermal conductivity, the previous day we discussed the thermal conductivity K, okay, kappa. So I wrote kappa, okay, as a thermal conductivity. This is basically 1 over 3 C V, okay, times lambda, again mean free path, times c average. Okay, so this c average is the average velocity, lambda mean free path. Now what is cv? Cv, so this cv is basically the heat capacity per unit volume. So there are various cv. Okay, so just the heat capacity or specific heats or the molar heat capacity. Okay, so the heat capacity, so this cv is the heat capacity per unit volume, per unit volume, okay, which can be written as cv equals to n times, is the number density small n, times c mole, right? So this is the molar heat capacity. Okay, so now if we write down in terms of, so this is the thermal conductivity K. Now I want to write this thermal conductivity in terms of temperature, right? Because the questions is given in terms of temperatures. The thermal conductivity at temperature T is K. Now at what temperature thermal conductivity doubles, right? So I want to study the temperature dependence of the thermal conductivity, right? So how the thermal conductivity depends on the temperatures. That is our aim. So here which quantities are depends on temperatures? Right. Cv. So first quantity, this is a constant, 1/3 is a constant. Okay, so this is a constant. So now the second, Cv. Cv depends on temperatures. And other one is lambda depends on temperatures, or C average depends on temperatures. Okay, so let's go one by one. So Cv is basically number density n times C mole. Okay. So number density is not depends on temperature, right? So basically n by v. So the number density is basically total number of a total volume. Okay. So this not depends on temperatures. Now lambda. So what is the expressions of lambda? So if you look into this eta, right? So basically I can write this as a kappa, actually 1/3, right? This is Cv, so I write as a n times C mole, right? But C mole I can write m over C mole over m, right? Times lambda times C average. So this C mole over m, right? So this C mole over m I can write as a 1/3, okay, and then n times m, this is basically rho equals to mn, just discuss, okay, rho equals to mn, and C mole over m I can write Cv over rho, Cv over, sorry, Cv over rho, this is the Cv over rho times lambda C average. So it can be written as kappa over eta, so where eta is the viscosity, so 1/3 rho lambda C average is basically Cv over rho, right? So that is important. Okay. So where kappa is the thermal conductivity, eta is the viscosity. So when we take the ratio, kappa over eta is Cv over rho. So that gives you, so this is the basically specific heat capacity. Okay, it's a small Cv, small Cv. Okay, so this is in capital Cv. So I just write a small Cv. So this small Cv is specific heat capacity, which is equals to small Cv, which is specific heat capacity. Now this specific heat capacity is a constant, okay, and it's independent of temperatures. So then the kappa and proportional to eta, okay, so basically at temperature dependent. So how eta depends on temperatures? So that means eta, how eta depends on temperatures? is basically lambda is independent of temperatures, so C average, right? So C average depends on temperatures, and that's why the eta depends on temperatures, and kappa is the same way, the kappa depends on temperatures. So then this is basically because of C average. Now what is the expressions of C average? From the Maxwell-Boltzmann equations, distributions, right? So if you calculate the Maxwell, the average velocity in the Maxwell-Boltzmann distributions. Okay, so recall the MB distributions and the average velocity. So the average velocity C average, so average or the mean velocity, C average is square root of 8 kBt over pi m, right? So that means C average is proportional to square root of t. This is important. Okay, I also discussed in the week one. Okay, in the week one teaching. So how C average is proportional to square root of t, because if you know these expressions, okay, recall these expressions, okay, and from these expressions it is easy to see that C average is proportional to square root of t. So therefore kappa, conductivity kappa, so this kappa, thermal conductivity, so this is also proportional to square root of t. Okay. So this information is needed to solve this problem. So at which temperature the thermal conductivity is double. Okay. So now you see that the kappa or the K is proportional to square root of t. So basically K1 over K2 equals to T1 over T2 square root. Okay. So therefore T1 over T2 is K1 over K2 square. So now K2 is 2K and K1 is K. So basically T1 is T and K1 is K and K2 is 2K. Now what is the values of, sorry, K1 is K, what is the values of T2? Okay. So just plugging this value here, so K over 2K square, right? So this is basically 1 over 4. So therefore T2 is 4 T1. So 4 T1 is basically 40. So T2 is 40, right? So therefore at what temperature the thermal conductivity is doubled? So it's 40, right? The last options. Okay, so at 40. So therefore the D options is correct. So in this case C options is correct. Okay. So it is clear. So if you have any questions you can ask. Okay, so please feel free to ask. Okay, any questions, any doubts? If not, then I will go to the next problems. Okay, so no questions, or you can also write in the chat box. Okay, so the third question is that calculate the radius of an oxygen molecule. Yeah, so calculate the radius of an oxygen molecule if its coefficient of thermal conductivity K is 24 times 20 minus 3 joule per meter second degree at 0 degree centigrade. So the information is that thermal conductivity is given at 0 degree centigrade. Okay, and the specific heat at constant volume Cv, this is given. Okay. Okay, so I have to calculate the radius of an oxygen molecule, okay, where the given is the thermal conductivity at 0 degree centigrade and the specific heat at constant volume CV. Okay, so what is the expressions of the thermal conductivity? So the thermal conductivity expression, okay. So again we first write down the thermal expressions of the thermal conductivity. So now problem number 3. So yes, the thermal conductivity kappa, again the thermal conductivity kappa, okay. So 1/3 CV lambda C average, right? So 1/3 CV lambda C average, right? So in this case there is so which quantity depends on the radius, or the, yes, which quantity depends on the radius of the oxygen molecules, okay? So we have to calculate the radius of an oxygen molecule. So the expressions of kappa is 1/3 CV lambda C average. So among these, which quantities depends on the radius of the oxygen molecules? So okay, so here what is the lambda? So this lambda is the mean free path, right? So that means this quantity must be depends on the radius of the oxygen molecules, right? Because mean free path depends on that. So what is the expressions of the mean free path lambda? So if you write down the mean free path lambda, the expressions of lambda is basically 1 over square root of 2 times pi d square times the number density n. Okay. So here n is the number density and pi d square is the diameter of the molecules, diameter of the molecules, right? So once you know the diameter of the molecules, the radius is basically d over 2, right? So diameter of molecules, and once you know the radius is r is basically d over 2. So first we calculate the diameter of the molecules. So now plugging this expressions of the lambda in the kappa, so in the equations 1, okay. So you can rewrite the kappa is basically 1/3 root 2, and what is this CV? So CV is again, yes, so CV is the heat capacity per unit volume, it's not the specific heat, okay. So we rewrite in terms of that. So CV m times small CV, okay. So this small CV is the specific heat, okay, times C average over pi d square, right, and n, and here also n. So because this CV is the heat capacity per unit volume, okay, and the specific heat is basically CV over rho, right? So CV over rho is the small CV. So small CV is basically the heat capacity per unit volume CV over rho, and rho is basically m times n, right? This one is a capital CV and this is a heat capacity, the specific heat capacity. So therefore this capital CV is basically mn times small CV. So mn times small CV, and there is also denominator, there is also n. So we cancel this n, this n. So left with these expressions 1/3 root 2 m small CV and then C average over pi d square, right? So up to this point is clear. Okay. So what the CV now is the specific heat capacity that is given in the problem. Okay. The values of the specific heat capacity given in the problems, and this capital CV, okay, is the heat capacity per unit volume. Okay, so if there are any questions, you can ask. Okay, so now we rewrite this diameter d. I want to calculate the diameter. So first we write d square. So d square basically m times again small cv. Okay. So here the cv is the denominator, v is denoted as constant volume. Okay. The specific heat at constant volume. That's why the v is in the subscript. Okay. So m times cv times c average over 3 root 2 pi kappa. Okay. Now the value is given, the kappa. What is the values of kappa? So if you look into this, in the problems, the kappa value, the values of kappa is 24 times 10 to the power minus 3, and T is also given because this is the 0 degree centigrade. That means T is 273 Kelvin. Okay, and the specific heat at constant volume, this is basically small cv. I use a small cv. So small cv is basically 20.9 times 10 to the power 3. Okay. So now the unit is important, joule per kilomole. Okay. So let us explicitly the joule kilomole degree, here joule per meter second degree. Okay. So I just copy these two. Yes, so this is the given. Yeah. So what is the unit? Unit is the joule per kilomole times degree. Okay. And what is the values of kappa? It's 24 times 10 to the power minus 3 joule per meter second times degree. Okay. Centimeter, right? So now if you see that the average velocity is not given, you have to calculate. M is not given, the values of kappa given, the values of cv given. So what is the, how to calculate the average or the mean velocity? Again we use the expressions from the Maxwell-Boltzmann distributions. So recall the expressions of the C average. So it's basically square root of 8 kBT over pi m. Right? So here also we, the values of m is needed, right? So what is the values of m? First of all, what is m? It's the molecular mass, right? It's the molecular mass. Now here, which molecules are uses? Is the oxygen molecules, right? Oxygen molecule. And you have to calculate the radius of an oxygen molecules. So what is the mass of an 1 mole of oxygen molecule? Right? So what is the mass of an 1 mole of oxygen molecule? Okay. So 1 mole of O2 molecule, oxygen molecule, O2 molecule, basically how much? 32 gram, right? So 1 mole of O2 molecules, how many molecules are there? Avogadro number, right? So it's basically Na, the Avogadro numbers of O2 molecules equals to 32 grams. Okay. So 1 O2 molecules is basically 32 over Na. What is the values of Na? 6.023 times 10 to the power 23, right? So the gram. So just calculate this. Okay, it's 5.31 times 10 to the power minus 23 gram. So I use SI unit, so it's basically 5.31 times 10 to the power minus 26 kg, right? So this is basically the M. Okay, 1 O2 molecule, the mass of 1 O2 molecules. Okay, so this is the molecular mass. This is the values of M. Okay, so now once you know the M and you know the temperature T is 273 Kelvin, what is the values of Kb? Kb is the Boltzmann constant, right? So what is the values of Kb? It's the Boltzmann constant, so 1.38 times 10 to the power minus 23, right? Joule per Kelvin. Okay. And your temperature given in Kelvin. So therefore, C average is basically 8 times 1.38 times 10 to the power minus 3 times 273 Kelvin, 0 degree centigrade, that means 273 Kelvin, over what is the values of pi? 3.14 times what is the values of M? 5.31. You just calculate 5.31 times 10 to the power minus 26. So all are in the SI unit. So it's the values of C average in SI unit. I mean the unit of C average. Okay, this is basically meter over second, right? So therefore, just calculate numerically using calculator. Okay, so it gives that 425 meter per second, right? So now once we know the values of C average, so that means we know this, and this quantity. So other two quantities are given. Okay, so it is straightforward task to calculate d square. Okay, so let's calculate. So the d square is equals to, then first the values of M. So 5.31 times 10 to the power minus 26 times CV, sorry, C average. So whatever CV or C average. So first write 425 and then CV. So what is the values of CV? Is given, right? Is 20.9 times 10 to the power 3. Now here is a catch. So 20.9 times 10 to the power 3 is joule per kilomole, right? So I converted it into mole, right? So 20.9 times 10 to the power 3, sorry, 10 to the power 3 divided by 32. So 1 kilomole of O2. So now I want to convert kilomole into kg. So 1 mole of O2 is 32 gram. Okay. So 1 kilomole of O2 is 32 kg. Right. So that's why I divided over kg, 32. So 1 kilomole, so I convert this kilomole to kg. So 1 kilomole O2 equals to 32 kg, because m is given in kg, right? And in d square there is a no kg, so d is basically length. So ultimately your unit in meter. Okay. So this kilomole and kg you have to cancel. So that's why first you convert kilomole into kg. So that's why divided by 32, and in the denominator we have 3 times, what is the values of root 2? Basically 1.41, okay, times 3.14, the values of pi. Okay, just look into the expression, 3 times root 2 times pi times k. So what is the values of k? Thermal conductivity is 24 times 10 to the power minus 3. So 24 times 10 to the power minus 3. So now what is the unit? Basically meter square. Okay. So if you use your calculators, and this gives, so it gives 4.6 times 10 to the power minus 20 meter square. Okay. So what is the values of then d? The square root of this is 2.15 times 10 to the power minus 10 meter, right? But the answer is given in angstrom, right? The answer is given in angstrom. Okay. So 1 angstrom equals to, if you convert the angstrom into a meter, is basically 10 to the power minus 10 meter, right? So 1 angstrom equals to 10 to the power minus 10 meter. So here I got, here I got 10 to the power 2.15 into 10 to the power 10 meter. So that means 2.15 angstrom, right? So 2.15 angstrom. So let's see this is in the option or not. 2.15 angstrom. So there is a no options, right? So where is the mistake? Right. So basically we want to we have to calculate radius, not the diameter. Okay. But I calculated diameter. Okay. So that means we divided by, I have to divide it by 2, right? So I calculate diameter d equals to 2.15 angstrom. But in the questions, okay, they asked to calculate radius. So what is the radius? So radius are basically d over 2. So 2.15 over 2, basically 1.07 angstrom up to 2 decimal place. Okay. So now see, now let's see this is the option or not. 1.07 angstrom. Yes, so the option is B, right? 1.07 angstrom. So the B is the correct options. Okay. Okay, so if you have any questions, you can ask. Okay, if not, then I move to the next question. Okay. So the next questions, the coefficient of self diffusions So the coefficient of self diffusion of oxygen at 273 Kelvin, again they are using oxygen, okay, and an 1 atm pressure, okay, is 1.28 times 10 to the power minus 5. So that is the coefficient of self diffusion, okay. Estimate the mean free path. It's a very simple problem. So the D is the diffusion coefficient, okay, is given 1.8 times 10 to the power minus 5 in SI unit meter square per second. Calculate a lambda, okay. At standard pressure 273 Kelvin, sorry, at temperature 273 Kelvin and the pressure 1 atm, okay, standard pressure, okay. So what is the expressions of the diffusion coefficient D, right? So how the diffusion coefficient D is related to your mean free path lambda? So the diffusion coefficient D is basically 1 over 3 lambda C average, right? So now lambda is given, sorry, lambda I want to calculate, D is given, but C bar is not given. The given is the temperature and the pressure. So this is basically we want to calculate, this is given. So to do this we want to calculate first C bar, okay, the C average, the mean velocity, right? So you already calculate the mean velocity of an oxygen molecule at 273 Kelvin, right, in the previous problem, right? So we just use this because the temperature is same, right? So yes, so at T equals to 273 Kelvin we calculate C average at these temperatures for oxygen molecules, because the mass of the M is the mass of the O2 molecules, this is same, okay. So what is the values of C average is 425 meter per second, okay. So I use this. So now C is given, this is basically 425 meter per second, right. So I want to calculate lambda. So it's very easy. So lambda equals to 3d over C bar, okay, the mean velocity. So 3 times d is 1.8 times 10 to the power minus 5 over C average. So this is basically 425. Now all are in the SI unit. So at the end, this is a lambda again is the unit of length, right? Basically it's meter. So use your calculator, that gives yeah, so 3 1.8, so it's 324, yeah, so it gives 1.27 times 10 to the power minus 7 meter. Okay. So let's check this is in the option or not. 1.27 times 10 to the power minus 7 meter. So first options, right? So the correct options is A. Okay. Okay, is there any question or any doubts? This is a very simple problem. So the left hand side is D is given and C bar we just calculate in the previous problem. Okay. Okay, if not, then I will move to the next question. Okay, so in the next question, is basically a molecule of methane, where the molecular weight is given 16, can be considered as a sphere having 5 times the volume of an argon atom. Okay, so one is the methane. So what is the formula of methane? Is basically CH4, right? And argon is Ar, right? Air. And the molecular weight is given. So one is 16, another is 40. What will be the ratio of the viscosities of the methane and the argon at STP? At STP, what is the ratio of the viscosities? Right. So in the first problem, we use the formula of the viscosity. So what is the expressions of the viscosity? And okay, so this is what are the option is given? CH4 is the methane, have considered as a sphere. So you can consider that the CH4 as a sphere, okay, having 5 times the volume of an argon atom. So what is the volume of a sphere? Okay, what is the volume of a sphere? Is 4 by 3. P is 4 by 3 pi r cube, right? So if volume is 5 times the volume of an argon, then the radius is basically, so we can rewrite in terms of diameters. Okay, so V is 4 over 3 pi r actually 2d cube, right? For d is the diameter, and V1 over V2 is basically 2 d1 over 2 d2, sorry, d1 over d2 cube, right? So that means your volume, this is basically 1 over 5. Okay, we can write this basically V1. Okay, so this is basically volume, how volume depends on the diameter. Okay, T1, T2. Now we use V1, 1 is the methane, so VCH4 over V argon. Okay, so VCH4 over V argon. Okay. This is basically 5 times volume of an argon molecule, so having 5 times, so this is basically 5, right? So the methane can be considered as a sphere having 5 times the volume of an argon atom. Yes, so this is the 5. Okay. So VCH4 over Vr equals to 5. So that means DCH4 equals to 5 over 1 over 3 times d argon. Right? The diameter of a methane molecule and the diameter of an argon molecule. Okay, DAR. Right. So this is on the things. Okay, and next. So this is needed to calculate the viscosities. Okay, so what is the formula of the viscosities? Yes, so the viscosity is basically 1 over 3 mn lambda C average. Okay, now what is the expressions of lambda? Yes, so lambda is basically 1 over root 2 pi d square. Here the diameter is needed. Okay, so you just rewrite in the one expressions. Okay, so if your eta is 1 over 3 mn lambda C average, this is basically 1 over 3 mn 8 kBT over pi m, right? This is basically C average times lambda, right? So what is the lambda? It's 1 over square root of 2 pi d square times n, the number density. So n cancel, right? So basically it gives, so left with square root of 8. So here is m, here is m, so 8m kBT over 3 root 2, okay, pi to the power 3 over 2. So square root of pi, this pi, so pi to the power 3 over 2 and then d square, right? So now the ratio of two viscosities, okay, so now I have to calculate the ratio of two viscosities, right? So eta CH4 over eta argon, right? So this is basically square root of, so kBT is fixed and these are the constant, so m is changes, so m CH4 over m argon, right, times, so this will be 1 over d square, so d argon square over d CH4 square, right? So now what is the molecular weight of methane and argon? So that is already given in the problem. It's 16 and 14, okay, and the diameter ratio, okay, we just calculate, we have calculated. So this is basically d argon over d CH4 is 1 over 5, sorry, 1 over 5 to the power 1 over 3. So yes, so d CH4 equals to 5 to the power 1 over 3 d argon. So that means d argon over d CH4 square is basically 1 over 5 to the power 2 over 3, right? Okay, please cross check if I have written wrong or right, okay? So please cross check this. So d argon square over d CH4 square is basically 1 over 5 per root of 2 by 3, and CH4 and argon is given, this is the molecular weight, so one is the 16, another is the 40. Okay, so 16 over 40 times 1 over 5 square root of 2 by 3, okay. So please cross check this, okay, that I put the data correctly or not. So it gives 0.216. Let's see this option is given or not, okay. So 0.216, yes, so the option B, right? So the B option is correct. Okay, so far any question? Okay, if so not any questions, then I will move into the next one. So there is a 5 more question left. Okay, so next question is very easy, I mean okay, so the next question is that the thermal conductivity of a gas assembly at a temperature T is K at a given number density N. What will be the fractional change in thermal conductivity if the number density is increased 3 times? Yeah. So first we have to know that how the thermal conductivity changes with the number density, right? If you know these things, you can just quickly answer this question. So how thermal conductivity changes with the number density n? Okay, so what is the expressions of the thermal conductivity? So the thermal conductivity kappa, right, 1 over 3 m n times lambda times C average. This is the expressions of thermal conductivity, right, times there is a CV. Okay, so let's check. So the expressions of the thermal conductivity, yes, so 1 over 3 capital CV lambda C average. Okay, so let's write in this form 1 over 3 capital CV lambda C average. 1 over 3 capital CV lambda C average. Right. Now how lambda is depends on the number density, because C average does not depends on the number density, right? The C average is basically 8 kBT over pi m. So here is a no n. So number density is the small n, right? So the number density is small n is basically capital N over V. So there is a no small n dependence in C average, right? Now this is the specific, sorry, this is the heat capacity per unit volume, right? This is a small n dependence, right? So small n is basically capital N over V is the number density, and this CV, so if you look into this problem, yeah, so this CV basically small n times C mole. Okay, so there is a small n dependence in the CV. Okay, but how lambda depends on small n number density, right? So lambda also depends, is a mean free path also depends on the number density, right? So if you, yeah, so here is the expressions of the lambda. You see that there is a small n. So when you multiply it, CV capital CV times lambda is basically small n times C mole, and lambda is basically 1 over square root of root 2 pi d square times small n. So small n cancel, right? Because kappa is proportional to capital CV lambda, so therefore there is a no dependence on n. So kappa does not depends on the number density, right? Because in this product, okay, n dependence is cancel out. Okay, so kappa does not depends on number density n. Okay. So thermal conductivity does not depends on the number density, small n capital N. It does not depends on the number density. Okay. So then what is the answers? What is the fractional change of thermal conductivity if the number density is increased 3 times? So thermal conductivity does not change, right? So the option is obviously D, none of the above. Right? The first option, thermal conductivity changed 25%, 50%, 100%. We just see that the thermal conductivity does not change. Okay, it actually depends on this. Okay, so then the option D is correct. Okay, so far any question? Okay, no question, then I will move to the next one. Yeah, so the next question, calculate the diffusion coefficient D of a hydrogen gas at 300 Kelvin temperatures and 1 atm pressure given the mean free path lambda. Okay. So first write down what are the givens. Okay, so lambda is mean free path is given 17.91 times 10 to the power minus 8 meter. So it is given in the SI units. Fine. Temperature given 300 Kelvin. It's perfectly fine, no need to change. And pressure is not needed because the diffusion coefficient D, okay, is basically 1 over 3 lambda C average, right? So here pressure is not needed. Okay, so only need the temperatures and the lambda. So once you know the temperature, we can calculate C average, right? So how to calculate C average? Again, just use this formula 8 kBT over pi m. Okay, the temperature is given, but the mass of so here the m is basically hydrogen gas. Okay, so what is the mass of H2 molecules? Okay, so we use this. So 1 mole of hydrogen H2 gas, okay, it's basically 2 gram. Okay, so then you just divide it by m. So m is 2 over Na. Okay, so 2 over Na gram. So you have to convert it to kg. So 2 times 10 to the power minus 3 kg. Okay, over Na. Na is the Avogadro number, right? So once you calculate this, once you calculate the m, then it can teach you to calculate C average. Okay, so then the values of C average for H2 hydrogen gas. So C average for H2 is basically square root of 8 kb is 1.38 times 10 to the power minus 23, right? Temperature is 300 Kelvin over pi is 3.14 times m, 2 times 10 to the power minus 3 over 6.023 times 10 to the power 23, right? Okay, so you calculate this. So the answer is 1781.97. Okay, so what is the unit? So it's basically velocity, right? In SI units, because I converted every quantity is in SI units. So 1781.97 meter per second. Okay, in SI unit, right? Okay, so then once you know this, that's the diffusion coefficient. So diffusion coefficient D is 1 over 3 lambda C average. So 1 over 3, what is the values of lambda? Lambda is given, right? Yes, so 17.91 times 10 to the power minus 8. So 17.91 times 10 to the power minus 8 times 1781.97. Okay, what is the unit? So this is meter and this is meter per second. So it's meter square per second, right? So the answer is basically this one is 3, 4. So 1.06 times 10 to the power minus 4 meter square per second. Let's see this is in the option or not. Okay, so 1.06 times 10 to the power minus 4. 1.06 times 10 to the power minus 4 meter square per second, option B, right? So option B is correct. Okay, so far any question? Okay, so if there is no questions, then I am moving forward. So the next question, yeah, how many questions are left? 3. Okay, time, okay, it's perfectly fine. So yes, in the next one is, so the hydrogen gas is kept into different container, okay, at pressure, temperature PATA, and another container at the pressure and the temperature is PB and TB, right? So if PB equals to 8 PA and TB equals to 4 TA, so there is a two container, in one container PATA, another container PBTB. Now how PB is related to PA is given and how TB is related to TA is also given. Then what is the ratio of the diffusion coefficient dB and TA? Okay, so they also mention the hydrogen gas in both the containers. Okay, yeah. So to solve this problem, so we first wanted to know that how the diffusion coefficient D is related to the temperature and the pressure. Okay. If you know this thing, you can easily solve this problem. So what is the expressions of the D? The diffusion coefficient. So D is the diffusion coefficient. It's 1/3 lambda C average, right? Okay. So you know how this C average or the mean velocity depends on temperature, right? You just see these expressions. So the C average is basically square root of T. Now how lambda depends on temperature and pressure. Okay. Yeah, from these expressions you see that the C average is not depends on pressure, right? So it depends on T, M and Kb pi are constants. A is also constant, is number. Okay. What is the expressions of lambda? So lambda expressions is 1 over square root of 2 pi d square and n, right? Now how n changes with pressure and temperatures, right? Or how pressure depends on number density n and temperature T. So you recall the expressions or the gas law. Okay, so basically the pressure P is n times kVt. Okay, right. So therefore n is pressure P over kVt. Okay, so put here, so basically lambda is 1 over square root of pi d square over T over P, right? And there is a kb. Okay, so kb. So therefore the diffusion coefficient D is proportional to T to the power, so this one is to the power half and this is proportional to T, so T to the power 3 by 2, okay, over P. Okay. Baki, sorry, all other things are constant. Okay, it's fixed because the diameter D is same. Okay, because we are using hydrogen gas in both the containers, right? So D is proportional to T to the power 3 and P. So how the diffusion coefficient varies with temperature and pressure. So this is needed, okay, to solve this problem. So once you know this, you just take the ratio. Okay. So dB okay. So now we know that how the diffusion coefficient D vary with temperature and pressure. So now there is a two container dB over dA is basically T to the power 3 by 2 P over TA to the power 3 by 2 and PA over PB, right? And all other things are constant fixed for both the, because the diameter same. Okay, this is, we are using H2 gas in both the containers. So only the vary is the temperature and pressure, right? So now this thing is given how P and PB related and TV and TA related. We just plugging these values here. So yes, so PB actually 8 PA and TB actually 4 TA. Okay, so PB 8 PA, TB 4 TA. So PB 8 times PA, right, and TB 4 times TA. So that means 4 to the power 3 over 2 and 1 over 8, right? So it's basically 1. Okay, so it gives 1, right? So that means dB is to dA, basically 1 is to 1. Okay, let's see this is in the option or not. Okay, yes, so the option D, 1 is to 1. Okay, so option D is the correct. Okay, okay, so far any questions? So first read the questions very carefully and let's see how the diffusion coefficient changes pressure and temperature. So you just, yeah, so you just extract this dependency and then plugging these values you have to calculate. So the same way you can solve various other problems. So the same trick. Okay, okay, so if there is no more questions, then I'll solve the last two problems. Yes, so the last one is, yeah, last two problems are quite big, but okay, it's fine. Yeah, there is almost 30 minutes left. Okay, it's perfectly fine. So okay, so far any question? Okay, if not, then I'll solve this one. So let's consider a container, okay, that divided by a partition with a small hole. So two container, let's try to draw a picture. Okay, so two container and there is a partition. Let's say there is partitions A and B. Okay. Also there is a small hole. Okay, so basically I will choose the containers and there is a partitions with a small hole. Okay, so I think this is a small hole. Okay, containing the same gas on each side. So A and B both are same gas. The gas on the left hand side has temperature T1 and pressure P1. So let's say we have both sides, the gas is A, in this case also the gas is A, but the temperature is T1, pressure is P1, and the gas on the right hand side is the temperature T2 and the pressure P2. If D is, so the diameter, the whole diameter is D, okay, so it's basically diameter, so diameter equals to D. Yes, so if D is much smaller than the mean free path, okay, the equilibrium is achieved by flux balance that I already discussed. Okay, it's a molecular flux balance if the mean free path is very larger than the whole. Okay, in that case, at equilibrium we get which one? Okay, pressure equal, temperature equal, P over T equal, or P over square root of T equal. Okay, this is very easy because we know that the equilibrium is achieved by the flux balance, right? So what is the expression of the flux, molecular flux? You just equate this, and if you know that how the molecular flux depends on pressure and temperatures, okay, then you will easily choose the correct options. Okay, so what is the molecular flux? So molecular flux phi. Okay, so what is the expression of the molecular flux? Yes, so molecular flux is basically 1 over 4 in the number density and C average. Okay. Now how n number density changes with pressure and temperatures? Just calculate, right? So how n is P over kBT, right? So then the flux, molecular flux phi is 1 over 4 pressure P over kBT, and what is the C average? C average is square root of kBT over pi m, right? Just put it here. So square root of 8 kBT over pi m. Then the flux phi is proportional to P over square root of T, right? Now how equilibrium achieved in this case? The equilibrium achieved by the flux balance, right? So that means phi 1 equals to phi 2. This is the flux balance in the both container 1 and 2. Let's say 1, this is the 2 container. So phi 1 equals to phi 2. This is basically flux balance because the process is a effusion process. Okay, so in any effusion process, the equilibrium achieved by flux balance. Okay, and the effusion process means that if there is a hole, okay, and the gas is leaking through this hole, okay, but the equilibrium is achieved, okay, through the flux balance. So phi 1 equals to phi 2, so that means P over square root of T1, so which is implies that P over square root of T1, P1 equals to P2 over square root of T2, right? So that means the option D is correct. Okay, option D is correct option. Okay. Okay. Yeah. So far, any question? Okay. If not, then I will go to the last problem. Okay. Yeah. So this is the last problem. So the problem is that the coefficient of viscosity of oxygen at STP. Okay, so the coefficient of viscosity of oxygen at STP is 1.96 times 10 to the power minus 4 gram per centimeter times second, and its molecular weight is given. M is 32. Oxygen we know. Calculate the collision cross sections of O2 molecules. Yes, So in the previous class, or maybe in the previous class, I will discuss what is the collision cross sections, okay, in details. So please have a look, and so today I will solve using this formula, okay, just because this is quite big, okay. So first we have to calculate the average velocity, right? So because viscosity is given, so what is the expression of viscosity eta? So the viscosity eta is basically, what is the expression of viscosity? Yes, 1 over 3 mn lambda c average. 1 over 3 mn lambda c average. Okay. So the viscosity is given, the molecular weight is given, calculate the cross section. So first we calculate c average, right? We already calculate the c average for oxygen molecules, right? Again, this is the temperature at STP, okay. So 273 kelvins, okay. So you already calculate the T equals to 273 Kelvin. What is the C average of O2, right? What is the C average of O2 at 273 Kelvin? I already calculate many times, okay. Yes, this one also use O2 oxygen molecules. So in this case the C average is 425 meter per second, right, at 273 Kelvin. So I use this, so 425 meter per second. Now in this case they are using so CGS unit, right, gram centimeter. So I convert into a centimeter. So 4.25 times 10 to the power 4 centimeter per second, right? It's clear or not? Okay, I just changes the unit, okay, meter to centimeter. Okay, so this is your average speed, okay, or average velocity of an O2 molecules. Right, this is the average speed of an, or the mean speed, okay, of an O2 molecules. Okay. Now how to calculate the number density? Because we know m, okay. So m is the mass of the O2 molecules, right? So mass of O2 molecule, so is the mass of O2 molecules, basically capital M over Na. So 32 gram. Now in this case I use CGS unit, so I just put in the gram. So 32 gram over 6.023 times 10 to the power 23, right, gives 5.31 times 10 to the power minus 23 gram, right? Okay. So M is calculated, C average is calculated. Now I want to calculate M, N, right? Okay, so eta is given in the problem. Okay, so next I want to calculate lambda. Well, I have to calculate cross sections, right, collision cross sections. Okay. So before first I have to calculate the diameters of the molecules. Okay. So if you know the diameter of the molecules, okay, then it's easy to calculate the collision crosses. Now among this, which quantity depends on the diameter of the molecules? Is lambda, right? The mean free path depends on the diameter of the molecules. So first I have to calculate n, okay, then I'm going to lambda part. Okay, so n is the number density, right? Number density, this is basically P over the pressure. Okay, so P over kVt, So they are using STP, so standard pressure. So what is the values of P? The standard pressure is 76 times 30.6 times 980, okay, divided by, so this is the standard pressure at STP, okay, divided by KBT 1.38 times 10 to the power minus 23 times 273, okay, but I have to use in SI units, right? So this is the values of KB 1.38 times 10 to the power 23 in SI units, okay, but I have to use CGS unit, okay, because everywhere I using the CGS unit, okay, so therefore we just changing this joule to CGS unit is 1 over 16, so 10 to the power minus 16, right? So it gives 2.69 times 10 to the power 19, okay, so it's the number density, so per centimeter cube or centimeter minus 3, so per centimeter cube, right? Because this is a number density, okay. So now I want to calculate lambda, right? So I know m, n is also known, and this is given. Now using this equation 1, okay, I want to calculate lambda. So lambda, the mean free path, is 3 eta over m times n times C average. Now 3 times eta is given. Eta is basically 1.96 times 10 to the power minus 4. Let's check the units, in which units the viscosity is given. The viscosity is given, yeah, so viscosity is given in CGS unit, okay. So it's fine. So 1.96 times 10 to the power minus 4. So no need to change the unit, because in every place I using CGS unit. So what is the values of m in CGS unit? 5.31 times 10 to the power minus 23. And what is the values of n in CGS unit? Yeah, so what is the values of n in CGS unit? Is 2.69 in 10 to the power 19, and the average velocity is average speed is that 4.25 times 10 to the power 4. So I'm just plugging this here. So 2.69 times 10 to the power 19 times 4.25 times 10 to the power 4, right? And the overall unit in CGS unit, so is a centimeter, right? So it gives 9.68 times 10 to the power minus 6 centimeter, right? Yes. So now once you know the values of the mean free path, so you have to calculate the diameter and then calculate the cross sections, collision cross sections. So how lambda is depends on the diameter? So lambda is basically 1 over square root of 2 pi d square times number density n. Right. So therefore d square is 1 over root 2 times n times pi times lambda, right? So 1 over root 2 times pi times n times lambda. Okay. Okay. So now we know that we just calculate lambda, okay, and we know the values of n. just plugging into here. So the values of D is basically square root of 1 over root 2 n times pi times lambda. Okay. So this is basically square root of 1 over 1.41 times the values of the root 2 times pi. Okay, the values of n, what is the values of n is 2.69 times 10 to the power 2.69 times 10 to the power 19. So I am using Fij's unit times values of pi 3.14 times what is the values of lambda, we just calculate 9.68, right, times 10 to the power minus 6. Okay. So it gives 3 times 10 to the power minus 8 centimeter. Right. This is the values of D. Now the collision cross sections is basically pi d square. So once you know D, the diameter, so the collision cross sections of O2 molecule, collision cross section of O2 molecule, okay. So the collision cross sections of O2 molecule is then pi d square 3.14 times 3 times 10 to the power minus 8 whole square, unit is centimeter square. So it gives 28 times 10 to the power minus 16 centimeter square, right? So let's see this is in the option or not. Okay, so 28 times 10 to the power minus 16, 28 times 10 to the power minus 16, yeah, so the option C. Okay, so option C is the correct option. Okay. Okay, so I solved total 10 problems, that is previous year assignment 3 problems. Okay, I think this year assignment 3 also very similar kind of problems, okay, like this today we solve. So I hope you can solve this year assignment 3 problems as well, okay, using these concepts, okay, and that we'll discuss today. Yeah, so if you have any questions you can ask. Okay, there is a time left 10 minutes, so I will maybe discuss some other things. Yeah, so if you have any questions you can ask. Okay, so if not, then I will discuss a basic on basic problems, that is basically is related to the thermal conductivity. Okay, how to measure thermal conductivity? Okay, so solve some problem where the thermal conductivity is given. Okay, in the various problems you see that the thermal conductivity is given this. Okay. But how to measure thermal conductivity? Okay, okay, so let's do on problems. So it's thermal conductivity. How to measure? So the question is that how to measure thermal conductivity, right? So let's consider two coaxial cylinder. Okay, so there is the questions how to measure thermal conductivity. Okay, so So let's consider two coaxial cylinder. So let's say this is one is the, so let's, yes, this is one of the cylinders, and let's say this is the cylinder A, okay, and along the same, so this is the axis, okay. There is another cylinders, right. So there is, let's say, and the cylinder, the inner cylinders both have a same axis, okay. So and the gas fill the space between the two coaxial cylinders. So this space the gas is filled, okay. So the gas filled in the space, so gas fill the space, okay, between two coaxial cylinders, between two coaxial cylinders, okay. Okay, I'm just coming in 2 minutes, okay, in 1 minutes. Okay, so yes, so the gas fill the space between the two coaxial cylinders. The inner cylinder, let's say, have radius A, and the outer cylinder has, let's say, radius is B, right. So let's use another color, so it's a B. So the inner cylinder radius A and outer cylinder is radius B, okay. And the outer cylinder is connected to a temperature bath, is connected to a temperature bath TB, okay, while the heat, so this is, let's say, connected to a temperature bath TB outer cylinder, right, and the inner cylinder, while inner cylinder, while heat generated, while heat is generated in the inner cylinder, generated in the inner cylinder, okay, at rate q per unit length, okay, at rate q per unit length, right. So the outer cylinder is connected to a heat bath, okay, at temperature TB, and the inner cylinder where the heat is generated in the inner cylinder at a rate q per unit length, okay, if the length of the cylinder, let's say L, okay, so its length of the cylinder, let's denote as a L, okay. So there is a heat source, okay, in the inner cylinder. Now what is the temperatures of the inner cylinder rises to T, right. So heat is generated in the inner cylinder, let's say that the temperatures of inner cylinder after some time, okay, it rises to TA, okay, and the outer cylinder has a temperature bath TB, okay. So then what is the rate? So the rate Q, okay, is basically 2 pi r times the heat flux, the radial heat flux. So this is the radial directions, okay. So it's basically 2 pi r is the radius, let's say we are considering a small patch, okay, where the radius is 2 pi r times this is ZR, okay. This is basically the heat flux, the radial heat flux. So it's the radial heat flux, right, is JR. So now the thermal conductivity is basically JR is minus kappa thermal conductivity times del T over del R. So how temperature gradient with R, okay, del T over del R, okay, and the left hand side is the heat flux, radial heat flux, that is related to the thermal conductivity kappa. So just plug it here. So it's basically minus 2 pi R times kappa times del T over del R, right. Okay. So now I have to integrate this because this is a derivative, so I have to integrate this. So Q dr over R, I have to integrate from A to B, right, because the inner radius has A and the outer radius is B, and I consider it, let's say at some R length. So I have to consider, let's say, at R, right. So this is basically at R length or at R radius. So this is an arbitrary radius R. So the heat flux is basically JR is 2 pi r times JR is kappa times del T over del R, okay. That gives you is minus 2 pi kappa k and integrate TA to TB, okay, times dt, okay. So then the thermal conductivity kappa is basically Q over 2 pi ln P by A over TA minus T, right. So this is the expression of the thermal conductivity. So once you know the temperature Ta and Tb, okay, and the Q, okay, is basically rate, then you can easily determine the values of the thermal, so you have to easily determine the thermal conductivity, okay, using this formula, right. So this is the way you can deduce the values of the thermal conductivity, okay, of a gas, okay. So basically we have considered two coaxial cylinder and gas filled in the space between the two coaxial cylinders, okay. And we have considered situations where the outer cylinder is connected to a temperature Tb and the inner cylinder where the heat is generated in the inner cylinders, okay. And finally the temperature of the inner cylinder as Ta, okay. And so you know these things, we can use this formula, okay. We can calculate the thermal conductivity. So kappa is the thermal conductivity. So thermal conductivity, right. Okay. So so far any questions? So far any questions from this class or from the previous class as well? Okay, so if you have any questions, you can also ask in the discussions forum, okay, that is also available in the course portal, okay. Okay, if not, then I will stop these sessions here, okay, and see you on next Sunday at 4 p.m. Okay, tada, bye bye.